Okay, we are going to begin by talking about thermochemical equations and also heats of reactions. Now, let's go ahead and just remember, um, just as a review, the things we talked about with calorimetry. There are some common errors with calorimetry, and they include the purity of the sample and especially the heat loss to the surroundings is typically a problem because uh, as soon as you put a hot object, it will radiate heat. No matter how good your insulation is, you will always lose some type of heat to the surroundings. So, good things to remember maybe for your exam. Okay, so let's keep going. And we're going to be talking today about the heat of a chemical reaction. Now, so as a chemical reaction is going, you are breaking and forming bonds. Now, that is uh, turning potential energy into kinetic energy. Now, the potential energy that is locked inside of those bonds is known as the enthalpy. Okay, that is what enthalpy is. Now, it has the letter H, and you can think of enthalpy as the measure of its internal heat content. And so frequently we use the symbol delta H to mean the change in enthalpy. So you'll see me use this in a second. So the enthalpy change is the difference between the heat content of the reactants and the products. And we'll do this a little bit more in a second. So the reactions can be endothermic or exothermic. So if delta H is negative, then the reaction is exothermic. That's because the change of energy is going down. It's releasing its heat. So that's negative, and that means it's releasing heat, so it's exothermic. If it is taking in heat, it is increasing the amount of heat, so it's positive, and so it's endothermic. So we show these on just as a review, we show them on the reaction profiles. This would be an exothermic reaction where you have the reactants and the products here. And now this guy is the activation energy, the distant or the change between the reactants and the top of this little profile, this little hump right here. Now, the enthalpy change is going to be the difference between the reactants and the products, okay? Now, in this case, it's going down because it's negative. So that's why we have a negative delta H. Now, exothermic reactions feel hot, like your hand warmers. Energy is released and they feel hot. They have a negative delta H. The energy of the reactants is greater than the products, and the heat is written as a product. Okay, so in these thermochemical equations, the way that we would write these is that we would have, there's two ways to write them. You can write the equation over here on the left like normal, and then you can write the heat content or the delta H, and you would put in a negative 802.34. Each reaction is its own numerical value. Or you could actually include it into the equation. Now that I've included it, it is on the product side because it is coming out of the reaction, so it is considered a product. Well, we don't put negatives in our chemical reactions. We put them as positives. We put plus signs. So it's actually still going to be a plus sign. It's just on the right side. Okay. So be careful with this plus sign. It does not mean that the delta H is positive. It just means that it's because it's on the right side, it is exothermic. Okay. So there's two ways to write that. So be careful with that positive sign. Now, endothermic reactions are the opposite. You have the reactants here, and the products, you are gaining energy, so it is actually becoming less stable because it is got more energy now. So remember that this hump now is the activation energy, and then this change from the reactants to the products is also the enthalpy change, the delta H, the enthalpy change. So it goes up, so it is positive. Endothermic reactions feel cold to the touch, like your cold packs now. And so that means that energy is being absorbed into the system. So it's being taken away from your hand. That's why it feels cold. It is a delta H, positive delta H, or greater than zero. The energy of products is greater than that of the reactants. And then the heat is written as the reactant. Okay, so in this type of equation, you have those two different flavors again. You can either write the equation here and then write the delta H and then positive 176, or you can put the 176 as a reactant over here. Now again, it's still a plus sign, but it's going to be on the left side now to symbolize that it is a reactant. Okay? Now, challenge question. Is an ice cube melting an endothermic or an exothermic reaction? Okay, so hopefully you gave it a little bit of thought about that one. So what happens when ice melts? It's going from a solid to a liquid. So where's the heat going? Is the heat going in or out? All right. Well, it is actually endothermic. That's because the heat is going from the surroundings and into the system because it has to heat up this ice, right? It is melting the ice. So the heat is going from the surroundings to the system, which is by definition an endothermic reaction. So people get confused because they feel that ice is cold, so they think it must be it's endothermic, but just stay with me. Always think about the surroundings to the system. So think about this one. Is water evaporation an endothermic or exothermic reaction? Well, again, is the heat going out or in? Okay, so it is an endothermic reaction. That is because the heat has to go into the liquid right here and turn it into a gas, right? So it requires energy for that to happen. So that is an endothermic reaction. So that's just a fun little mind twist to make sure that you understand what an endothermic and an exothermic reactions really are. Now, let's use some thermochemical equations. Each reaction will have its own unique enthalpy. We can predict the energy released or absorbed based on the amount of the reactant available. And that's going to include stoichiometry. Yay. Well, and this makes sense because, one drop of gasoline is going to, emit less amount of heat than one can of gasoline, right? If they're both burned. It would be the same chemical reaction, but obviously the more gasoline that you have, the more heat that you'll create, right? So we can relate mass into the amount of heat that we're going to evolve, okay? Hooray! Okay, so let's just take the simple combustion of water or the formation of water, and it has its delta H value as negative 483.6 kilojoules per mole. Now that's saying that for every reaction here, it is negative 483.6 kilojoules for every mole of this whole reaction. So how much energy would be released if 500 grams of water is formed? Okay, so if we formed 500 grams. Well, let's start with what we know. This is typical stoichiometry, 500 grams of water. And then let's go ahead and change grams into moles because you know that grams are not useful in chemistry. Now that we have the moles of H2O, we can actually change the moles of our substance into our kilojoules right here because this is kilojoules per mole. You see that? Now this is kilojoules per reaction basically. So what you're going to do is you're going to take, put the moles down on bottom, and you're going to put your kilojoules on top. And now what's going to happen, what's funky about these different types of reactions is that you won't always put a 1 here. You're going to put this 2 right here. And I'm going to work out my math here. And I'm going to get negative 6,716 kilojoules, which rounds to negative 6,720 kilojoules. Okay, so you might be asking yourself some questions. This negative 483 came from right there, all right? And then this 2 comes from right there because there are 2 moles of water produced. So that is the what you're going to have to do, okay? Everybody should be cool on this step. So then you just have to convert moles into kilojoules just by doing this, okay? Let's try another example. Here's your propane, C3H8 plus O2 yields CO2 and water. It's the combustion of propane. And it has a delta H of negative 2,219.2 kilojoules per mole. If 5,000 kilojoules are released, what volume of oxygen would be consumed at STP? So lots of good areas of chemistry here. We have 5,000 kilojoules are released. And then so we'll take our kilojoules and we'll convert kilojoules into moles of O2. Now notice that you have negative 2,219.2. That came from the delta H right here. And that's how many heat units per reaction. Well, in this reaction, we had 5 moles of O2. So that's why we have to put 5 moles right there. So then we are going to convert moles into liters. We remember that 22.4 liters is 1 mole. And then it is negative 252.3 liters. All right, good. So does that make sense? Hold on a second. Does that answer make sense? Do you have a negative volume right here? No, it doesn't. So let's hold on a second. Let's take a look at this. Remember, it was negative 5,000 kilojoules are released, okay? So that actually should be negative right there, which is going to cancel out this negative and then make our final answer positive. So that is what makes the difference. You really have to pay attention to your signs on this unit because it's telling you if something is released, then it's exothermic. If energy is absorbed, it's endothermic. Okay, so you have to pay attention to either positive or a negative. Now, again, that's where the 5 came from. That's where the 2,219.2 came from. Okay, we'll get one last one in here. We'll have 14.4 grams of magnesium is burned in excess nitrogen at constant atmospheric pressure to form Mg3N2, magnesium nitride. 136.7 kilojoules of heat is given off. What is the molar enthalpy of formation, aka molar enthalpy, of Mg3N2? So what I'm asking for is the kilojoules per mole of that. So what I need to do is I now need to find the amount of moles, right? I have 14.4 grams of magnesium. Go ahead and convert that to moles. Just divide by the molar mass. That's G stands for go to the periodic table, and I will find 0.593 moles of magnesium. Now all I have to do is take kilojoules, the amount of heat that's given off. That's the amount of heat that was given off per this many moles, right? So let's change that to a proportion of how many per 1 mole, right? How many kilojoules per 1 mole. And so all I need to do is take my kilojoules, 136.7 kilojoules, divide it by the number of moles, and I will get 231 kilojoules per 1 mole. Okay, that's essentially all I'm trying to do here. And so that will ask us something. Now then you have to think, is this going to be positive or negative? Well, heat is given off here, so that must be exothermic, so that's actually going to be negative 231 kilojoules per mole.